So Beth, at what time should I start?
I'm sorry, I was multitasking. You can go ahead and start now. Looks like we've got 10 attendees.
Okay, good. So thank you everyone for joining this talk in this talk series for this summer. My name is Matt Grau. I'm a professor in the physics department at Old Dominion University in Norfolk, Virginia. And my talk's about searching for new physics, looking for symmetry violations. So I'll give an explanation of what I do before I actually talk about what symmetry even is. I'm an AMO experimentalist. So AMO stands for Atomic, Molecular, and Optical Physics. And what that practically means is that I work with atoms and molecules and light. So I use lots of lasers and put atoms and molecules in ultra high vacuum chambers and work with small numbers or even single atoms at a time. And I use these as very precise and delicate systems to probe fundamental symmetries of nature. So for instance, here's this is a picture of my lab. This is a prelude because after this talk, we'll go in and walk around for a while and I'll show you different things that we have set up. But we have some lasers and vacuum chambers and mirrors and lenses around, and it's just a good amount of fun. But then what we try to do is inside the experiment chamber, we get things like this. So this is 7 individual atoms that are levitated in space with electromagnetic fields. And that by itself, I think, is very cool. But then we can use these atoms as sensors to look for new types of physics, new particles and new forces. Okay. So to come to the title of my talk, which is about symmetry, here's a quote by Phil Anderson, who won the Nobel Prize in Physics back in the 70s. He said, "It's only slightly overstating the fact that physics is the study of symmetry." So physics is the study of many things, but really central to a lot of it is symmetry. So what is symmetry? We'll talk about that. Here's the outline. I'm going to discuss what that is and then talk about different types of symmetry and then what it means to violate symmetry and how this can be a useful way to learn about the universe. We'll talk about something called the matter-antimatter asymmetry problem. And then ways that we can try to solve this problem and experiments that have been done to try to answer it. So symmetry is whenever you have a physical system, just some stuff that is unchanged by a transformation. So I like to think of Wile E. Coyote chasing Roadrunner. They're on this long, infinite road, and they always keep moving forward. And any spot in the road is the same as any other spot. And the coyote can never catch the Roadrunner because it's always the same. Right? Or another thing would be just a sphere or a ball. If you rotate it, it looks the same. You can't tell if the sphere is rotating or not because it's symmetric, right? So compare that to some physical systems that don't have symmetry. So if, for instance, Wile E. Coyote runs off of a cliff, this symmetry is broken and he falls. Yeah? Or if our sphere instead is some sort of weird polygon, then if we rotate it, we could tell because there's different facets to it, okay? And this is a useful concept in physics because it means that we can use the same physical law to describe many different situations. So here's an example. There we go. So an example is Coulomb's law, which is the electromagnetic force, and it's what causes 2 charged particles, a positively charged particle and a negatively charged particle, to be attracted towards each other, right? So we have an equation that describes that, and we say the magnitude of this force is equal to the product of the 2 charges divided by the distance squared times some prefactor that tells us how strong this force is. But what's cool is that this force can describe not just these 2 charges in this configuration, but it can describe the same exact similar physical situations that may look very different. So for instance, if I put these 2 charges, maybe it's a proton and an electron, at the origin of some coordinate system, right? And if I move them, it looks the same, right? The only thing that matters for the force is the distance between these 2 particles. So, or I can move it down here, right? So that same equation and even the same force will describe these 2 particles no matter where they are. So I can put them anywhere in space and it still works. So we say it's the symmetry of translation exists in this problem. Another good symmetry is rotation. So if I take my two particles and rotate them a little bit, the physical picture hasn't really changed. The only thing that matters to this is the distance between the two of them. So this is another good symmetry. And it means that as long as these two charges are the same distance apart, that same law describes them no matter where they are or how they're oriented. Okay. Another useful symmetry of this problem is the charge. So I'm going to call it charge conjugation. We can replace these charged particles with the same particles but with opposite charges. So if I have a negatively charged particle and replace it with a positively charged particle, and replace my positively charged particle with a negative one, well, because this force is equal to the product of the two charges, all that matters is the relative sign of these two. Right, so if one's positive and one's negative, we're going to get an attractive force. So if I replace them with their inverses, both of these become negative, but those negative signs, -1 times -1 is +1, and the equation remains unchanged, but we're still describing the same situation. So we can describe different types of particles as well. So the sign of the charge is a good symmetry of this problem. But this is different from the other symmetries we were talking about before, because those were continuous. They described changes that could be incremental, or we can make small changes, we can move them around. There's lots of different positions, whereas charge is more of a switch. It could either be positive or negative. There's not a continuous gradient in between. And these discrete symmetries, as we'll see later, can sometimes tell us some very interesting things about nature and reality. Another interesting symmetry is something called parity. So this is the symmetry of reflections. So if your physical system looks the same as its mirror image, or what it looks like in the mirror, then we say parity is a good symmetry. So for instance, I can take the position of all my different charges and I can reflect them through the origin. This is different than a rotation, because there's not actually a good way you can't actually go to a mirror image by just a rotation. You have to do a rotation plus a inversion, where you sort of turn everything inside out. So mathematically, what that looks like is if we take our coordinate axes and we take x, which points in this way, and if we point it in the opposite direction, and y from this direction to the opposite direction, and z to the opposite direction. And if when we do that, the physical system remains the same, then we say parity is a good symmetry. And this is nice because for most physical laws, parity is a good symmetry. Stuff behaves the same as it does in the mirror, right? That's why if you look in the mirror, you see a mirror image of yourself, but it looks also like a human being that behaves in a way that you expect, right? If your mirror image was, a Martian, then parity would not be a good symmetry. And well, yeah, the mathematical equation that describes this is you take all of your different coordinates, so time remains the same, but x, y, and z go to -x, -y, and -z. And this parity transformation sort of takes you from one universe to a mirror universe where all the physical laws remain the same, or do they, right? So if you've seen this television show from, I don't know when, they explore the mirror universe where everyone behaves very differently. So maybe our universe is like that. Maybe when we invert parity, all the physical laws change in mysterious ways. So this Coulomb interaction, the electric force, also is invariant under parity. So if we invert our coordinate axes, we basically take the two particles and switch their locations. So r goes to -r. Well, the -r times -r is still +r squared, so it's the same. So this electric force is also symmetric under parity. So it's very symmetric overall, right? I've showed you a bunch of different transformations that really don't change what's happening. And this is great because it means that situations where the particles are here, or they're rotated, or where they've been swapped, or where we've changed the sign of their charges, can all be described in exactly the same way. And this saves a lot of time. We just need one equation. And it also means that we can, when we're trying to solve physical problems, exploit some of these symmetries to make our solutions simpler. So one question is that you might be thinking of, or that I think of, is, are these symmetries just always true everywhere in nature? And in your experience, you might notice that some of them are, right? Like we do look like our mirror images. The electric force I just showed you is super symmetric in lots of different ways, right? But these symmetries, in particular, parity and charge conjugation, are not actually true symmetries. Not every physical law obeys them. Some of them behave differently under their mirror image, which is really weird. Like I find that counterintuitive because things that I look at look the same in their mirror image usually. I can't find a lot of examples around me that look different under mirror image. Oh, there's some. For instance, like my left hand, when I look at it in a mirror, it actually looks like my right hand. So sometimes we call this symmetry handedness because left-handedness goes to right-handedness and stuff. But many of our physical laws do obey these symmetries. So for instance, we used to think that parity was a good symmetry for everything because every sort of physical law we looked at obeyed the symmetry. But there was a mystery which was called the tau theta puzzle. So when people were discovering some of these fundamental particles, there was two different particles. There's a particle called a tau plus, so it had a positive charge, and a theta plus, and it had a positive charge. And it was weird, they had the same charge, they're both positively charged, and they, as far as we could tell, had the same mass, which was very coincidental because most of the particles we have pretty different masses. But they decayed in two different ways. So tau plus decayed into three different mesons that were positively charged and two that were neutral charged. And it decayed with an odd parity. And theta plus decayed into also a charged plus meson and a neutral one, but with an even parity. So it's weird because if this was the same particle, we typically can also define certain parities or handedness. So all particles are either left-handed or right-handed. But this was two different particles, one that was left-handed and one that was right-handed, that otherwise seemed like they were the same. And if parity is a good symmetry, this shouldn't be allowed to happen. So the problem was we see these two different decays. It looks like if parity was not something that we were concerned with, they would be the same thing. But the same thing is decaying into sometimes positive parity and sometimes negative parity, sometimes left-handed and sometimes right-handed. And there wasn't a good explanation for that. People said this, well, it's so weird that these two particles have the same mass, right, when they have different parities. But then some theorists turned that on their head. They said, well, what if it's the same particle and parity is just not a good symmetry, right? Which at this point was very revolutionary because every physical law we had seen until this point said that it was a good symmetry. But they worked through the math of it and said, yeah, okay, if parity is not conserved, if it's violated, maybe just sometimes, then we could observe this sort of physical event. So is there any other way we could test this, right? So if you ever have a physical theory, whether or not it's true, I mean, no matter how nice the math looks, it's determined by if you do an experiment, if the experiment also agrees with that theory. So they recruited an experimentalist at Columbia, Qingsheng Wu, who she dealt with beta decay. So when nuclei decay into beta particles, which are high energy electrons. And she did an experiment where she took a cobalt nucleus. So cobalt nucleus has a spin, it points in a particular direction. And she did two different experiments where she took the cobalt nucleus and the spin was oriented in one direction, say up, and looked at the beta particles that came off of it, and then flipped it over and then did the same experiment. So she did an experiment with its mirror image and then tried to see, okay, do we get the same result? So she would orient the cobalt nucleus relative to some magnetic field, right? And then measure how many electrons it decays into because it's not a stable nucleus. And did this experiment under two conditions, oriented with the magnetic field and anti-oriented. So this corresponds to a mirror image. And tried to measure, do we see the same number of beta particles or electrons emitted? And actually, she saw that they didn't. So what this experiment looked like was normally if you just take cobalt, it will decay, you'll see electrons coming off of it as it decays into nickel. An electron is emitted and also a neutrino and some photons. And So she measured it. You can't really see neutrinos because they don't interact very strongly with anything, but you can see electrons and photons very easily. I mean, we see photons all the time. So she put cobalt, and the spin here was aligned up, and there's a magnetic field created by a wire that twists around the nucleus and creates a magnetic field at the center of the wire. So here, the magnetic field's pointing up, the cobalt spin is pointing up, and they look where the electrons are emitted and where the photons are emitted, right? And then they look at the mirror image of that experiment. Basically, they run the current in the opposite direction to change the direction of the magnetic field. And they also then look which way are the electrons emitted, which way are the photons emitted. And they see, that's what's being plotted here, a slight discrepancy. Actually, it's a pretty big discrepancy. It's, you know, something like 20%. So they see a huge amount of contrast between the amount of electrons being emitted in one direction versus another, showing that it really, this experimental setup really does matter, you know, which orientation the nucleus has. It actually violates this parity symmetry, which was surprising because until this point, everyone thought just every single physical law, every sort of decay would follow this. So as it turns out, electromagnetism just by itself, that obeys that's symmetric under parity. If you take the mirror image, it looks the same. But the weak interaction, which is the force that describes how a particle decays from, for instance, cobalt to nickel and emits an electron and neutrino, that violates parity. So when cobalt decays into nickel, 3 different particles come off: an electron, a photon, and a neutrino. And the relative directions of all of those matter. And if you change if you take the mirror image of your experiment, then actually the same relative direction, they still come out in the same relative direction. It's very weird. I can't really understand it, but that's how the universe works. That's what we've measured. So we know that it's real. In fact, I mean, this experiment was so weird that when it was first published, Wolfgang Pauli, who was a very famous theorist, for instance, the Pauli exclusion principle is named after him, said, this is total nonsense. Like, that doesn't make any sense because it violates parity, and how could that be, right? But as people looked into it more and more, I mean, now we're absolutely certain that, yeah, he's wrong, parity is violated, the experiment is right. And what's neat is this is a really good way to probe fundamental particle interactions because it's, well, I don't know if you can see on my slides the dates on these papers, but here, the time when the theorist proposed this in 1956, the experiment was published in 1957, and it was actually less than a year later, right? So this looks like a pretty big lab, and it is, but I mean, it's about the same size as my lab, as we'll see at the end of the talk. So it's minuscule in comparison to things like the Large Hadron Collider, which are miles and miles of tube, and thousands and tens of thousands of people work there, and they're very expensive. And that's the other avenue we have to discover new types of physics. This is a relatively small scale, low cost, low energy, easy, not easy, they're very hard experiments, but completely different scale, but they still have huge discovery potential because of how precise they can be. Another interesting thing about this parity violation is it solves this philosophical problem called the Ozma problem, which is if you're trying to communicate with aliens and you didn't have any way to send visual pictures, right? You just could send information. How could you describe what is left-handed and what is right-handed, right? How could you describe these 2 different directions? It's a very visual, spatial thing, and you can't just do it with words. But what you could do is say, oh, well, if you have some cobalt-60, go get it, put it in a magnetic field, and look at which direction the electrons come off when it decays. And then you can define left-handed versus right-handed. So is that useful? Well, if you ever are communicating with aliens and you need to tell them what is left and right-handed, you can. So that helps me sleep better at night. So coming back to our symmetry, our outline, we've talked about symmetry, parity violation, and the magnificent experiments by Ching-Chun Wu. And now I'm going to talk about a new problem with symmetry, which is the matter and antimatter asymmetry problem. So antimatter is, well, matter is the stuff that all of us are made out of. It's particles like electrons and protons and things. And antimatter is similar particles. They're the same in every way, except the charge has changed. So an electron has what's called an antiparticle. It's an anti-electron, and it has the same mass, the same spin, all the same properties, except rather than being negatively charged, it's positively charged. Sometimes we call it a positron, but I'll call it an anti-electron to make it clear. And the reason why you maybe haven't heard about anti-electrons and maybe haven't interacted with them in your life, for instance, electrons are just flowing in the wires in the wall and in my computer, but positrons or anti-electrons are not. And it's because when an electron and an anti-electron meet each other, they annihilate explosively. So they release a lot of energy, and they both disappear. So this is called particle-antiparticle annihilation. And that's why if you have a bunch of matter around, you typically won't have a bunch of antimatter around because it's not a very stable environment to be in. The reverse can also happen, right? So in this case, time is a good symmetry, whether or not things happen going forwards or backwards. So we can run the process in reverse. We can start off with a bunch of energy or photon, and then that spontaneously can produce a particle pair, an electron and an anti-electron. And this is really useful, for instance, if you wanted to make a universe, right? If you wanted to make a universe, you could start off with a bunch of energy and like some sort of bang, right? Called a Big Bang. And after this, you'll have a bunch of photons around in your universe. But what you want is matter. You want to make stars, you want to make planets, you want to make people. So all these photons can produce particle-antiparticle pairs. So we'll have them and they'll start to produce these electron-anti-electron pairs, and also proton-antiproton pairs, and all sorts of other particles and antiparticles. This is called pair production. The problem, though, is because this process is symmetric back and forth, that eventually all of these particles will start to annihilate with each other, right? And you'll just be left again with a bunch of energy and not any stuff to make your universe out of, which is a problem because, well, one, from my experience, the universe is made out of stuff, right? I'm here, there's a bunch of particles in me, in the room I'm in, and the planet I'm on, and the galaxy I'm in. And I don't really have a good explanation for where that is based off of all the fundamental microscopic physical laws that we've measured, which seem more or less symmetric in this way, right? So this is the matter-antimatter asymmetry problem. And it may seem aesthetic to you, right? But the problem is that we expect equal amounts of matter-antimatter in the universe, but we don't see that. We see predominantly galaxies made out of matter, and we don't see a bunch of antimatter galaxies around. So you might say, well, what's your problem? The universe is just made out of a bunch of matter. But the problem is, I have a bunch of physical laws that I've measured, not just me, but everyone, very precisely. Tens of thousands of scientists have characterized all these laws at great expense, spending billions and trillions of dollars. And we have a very good idea about how these fundamental interactions work. And some of them, we can match them up to theory at the 13th decimal place. They're incredibly precise, and yet they cannot explain why anything in the universe exists at all. So it's this huge discrepancy, and this does cause me to not sleep at night. Okay, so there is a proposed theoretical explanation for this. Andrei Sakharov, Nobel Prize winner from 1975, said, well, if you have symmetry violation, this could cause it, right? So you need a different type of symmetry violation. You need to be able to, that time process where you can have time going forward and backwards, you need to be able to violate that. And if you can do that, then you can produce matter and antimatter at different rates. And then you can have some more matter left over. So that way, when all of your different pairs annihilate, you'll be left with a bunch of photons, but a little bit of matter. And that matter can find itself and form, galaxies and planets and stars and humans. So what it looks like is when you form your universe, you make a little bit of excess matter, right? You might be able to see it in this picture, you might not, but then as my particles start to annihilate, I'm left over with a few different bits of matter. And that's fine, because that looks like the universe. The big problem is that, the laws that we've measured, they don't have enough ways to violate this fundamental symmetry to be able to generate this excess amount of matter. So we don't know what sort of interactions could cause you at the sort of early stages of the universe to create this excess matter. So the general idea is that you have at very high energies some new particles or new forces that can interact with these particles in different ways and generate this extra matter. But we've never seen them because the way that we look for particles, there's sort of two different ways. One is in a collider, you just slam things together at higher and higher energies, and any sort of decay particle that can be produced will be produced, and you look for those. So if you're trying to look for new particles at high energy, you just need to slam things together at higher and higher energies and look and see what you get. Problem is we've done that for a while and we haven't seen anything. The other way is you can look for, kind of like the cobalt experiment, you can try to set up an experiment and flip rather than flipping parity, look at the mirror image, sort of run it backwards in time and look for symmetry violation that way. And that symmetry violation would also be the herald of sort of new particles and interactions at higher energy scales that you couldn't normally be able to access. So an interesting way of doing that is to look for something called the electric dipole moment of the electron. So the electron, I described it before, it's a charged particle, it has a spin, right? And that spin interacts with the magnetic field, but what is the shape of the electron? And it could be spherical, in which case it wouldn't interact with an electric field other than just to be pushed around. But if the electron were lumpy, right, if it were kind of shaped like an egg, then the electric field would tip it over the same way that the magnetic field would tip over it due to its spin. So if it did have a shape that was non-spherical, then this would violate both parity and time symmetry. The way to see this is, so here's an electron and I've shown it has some sort of egg shape and a spin. And if you run time backwards, then the spin changes direction, but the shape of the electron doesn't. And here you'd have to sort of flip this over. You could also, if an electron had a non-spherical shape, this also violates parity, because if you did a parity inversion, then the sort of direction that the egg is pointing in would flip, but the direction of the spin would flip. And these electrons look different. As far as we can tell, there's only one type of electron in the universe. So that's what we're trying to look for. We want to try to measure the shape of the electron. And if it ends up being not spherical, then that's the indication of the type of symmetry violation that we need to explain why there's matter in the universe. The way that this works practically is we take the electron and we prepare it in a specific spin state. So we maybe take it with spin pointing down in a magnetic field. And in the magnetic field, the spin interacts with the magnetic field. So if the spin's pointing down versus up, we have two different energies, right? So what we do is we start off and spin down, and then we shine in like a laser or a microwave or something, and we change its frequency. And when the energy of the photon we're shining in matches the energy difference between spin down and spin up, then the probability to measure the electron later and see it in spin up looks like this. So here we're changing the wavelength or the energy of our photon. And once our photon energy matches the energy between spin up and spin down in the magnetic field, we'll see a high probability for the electron to be in spin up state rather than the spin down state. Okay, and that just tells us how strongly the electron's interacting with the magnetic field. Now, if the electron has a shape to it and it's in an electric field, then what happens is these two energy levels get split apart a little bit more. When the electron is spin up, the energy level gets a little bit higher, and when it's spin down, right, the shape of the electron makes the energy a little bit lower. And what that means is that this energy level, when we do this experiment, this shape of our experiment, it shifts over to the right. And if we then change the direction of the electric field relative to the magnetic field, rather than this situation, the energy levels shift closer together. So this peak would actually shift down to the left. So what we do is we put the electron in an electric and magnetic field, and we change their relative orientations, and we look for our spectroscopic signal to jump back and forth. Okay, and that would be the signature of the symmetry violation, which we need. So practically how we do this measurement, well, we want to measure a bunch of different times, have a bunch of different experiments so we can have really nice histograms for these different peaks to be able to resolve them really well. We also want to have a large electric field, because the larger the electric field, the further the splitting between these two gets. So we want a really large electric field. And then we also want to measure for a long time. The longer we measure, the narrower these peaks get, because the name of the game is we're going to try to resolve the energy difference between these two peaks. And because the symmetry violation is small, they're not going to be shifted by very much. So we need a very precise measurement to be able to see this. One of the really good tricks that we use in AMO physics, the M stands for molecules, is we use molecules. We put the electron in a molecule, and inside a molecule, we have access to really the largest electric fields that you have anywhere on Earth. Normally, if you want an electric field, you take two pieces of metal and you make one positively charged, you put it like 100 volts, the other negatively charged at minus 100 volts, and you get a very large electric field in between them. And you get a larger and larger electric field the closer they get together. But the problem is that as they get too close together, because there's microscopic roughness, you're actually going to get lightning bolts. You get electrical discharge between the two of them. Electrons will hop from one to the other, and then your electric field will break down. So there's a practical maximum to the size of the electric field you can make, which limits the sensitivity of the type of experiment you could do. We go past this by using nature's electric field plates. We use a positively charged ion and negatively charged ion that are bonded into a molecule. And in between them, we get immense electric fields that are thousands to millions of times larger than anything we can make in the lab. And because sort of atoms are perfectly smooth, fundamental objects, they don't have these discharges occurring. So we can get hundreds of gigavolt per centimeter per centimeter electric fields inside of a molecule. And this gives us sort of the absolute sensitivity, the extreme sensitivity we need to be able to look for these very small symmetry violating signatures. So I'm going to talk a little bit now about an experiment that was done pretty recently at the University of Colorado, where they put an electron in a molecule called hafnium fluoride. For technical reasons, they had to whip this molecule around in a circle to be able to sort of align it. And then they looked for these small energy shifts. And they did this measurement for about a year, and they just did it really, really well. And spoilers, they basically found no evidence of symmetry violation. Now, this is sort of a cool artist picture of what this experiment looks like. What it practically looks like is there's just a bunch of stuff, a bunch of wires and tubes in the lab. It's a huge mess. And you'll see my lab, it's also a big mess. But somewhere inside of this metal chamber, and this is about, this big. So it sits on a tabletop, and it's inside of one room, and it's operated by a team of like 7 people. So it's not a crazy, huge undertaking, although it is very complicated and very challenging to get it to work, because on any given day, there's like 12 different lasers here. The probability of any of them being broken is like 10%. So take 10% to the 7th, 1 minus 10% to the 7th power, like it's not working most of the time. You need to be actively fixing everything constantly. Yeah. So what they found by doing this type of measurement was that the electron was extremely round. It's the most precise measurement of the shape of the electron ever. And they found that the EDM, the electric dipole moment, is 4 times 10 to the minus 30 electron centimeters. What that means, if you were to have the electron, if it were the size of the Earth, right, it would be so round and so smooth that it would be a perfect sphere. To the point where you could take one coronavirus molecule from one side of the Earth and put it in the other, and that's the sort of limit of how smooth and round the electron is, right? So obviously much more round than the Earth is, but also not out of round enough, not misshapen enough to be able to explain why we see this excess matter in the universe. So this was a very cool experiment. I encourage you to go read this paper from last month in Science. So the summary, symmetry is very interesting and important concept in physics. We use it to simplify problems, and we exploit it to be able to search for the signatures of sort of new particles that otherwise we would need very large and expensive apparatus to be able to try to detect. And so far, tabletop precision measurements, which search for these types of symmetry violations, haven't found any explanation. So with that, I'll take your questions, and then after that, we'll go across the hall into my lab, and I'll show you, what an AMO lab looks like and the sort of things that I do. Right. So I will get set up now to go into the lab and take you on a little virtual lab tour. While I'm doing that, you can start to ask some questions. And I'll answer them during the tour and also afterwards. I have one question, which is there any correlation between the symmetry in physics and the abstract definition in mathematics group theory? Yes, there is. So many of these symmetries are the same. Now, I'm a experimentalist. While I use group theory sometimes, especially to describe some spectroscopic systems, the sort of fundamental discrete symmetries I'm interested in are sort of, I'm not actually sure what the group theoretic description of them are, or even if there necessarily is one. For instance, I don't know if like time reversal symmetry has a symmetry group associated with it. So I guess maybe the real answer is I don't know. Another question is there any way that antimatter and matter can exist together? And yeah, there's a couple ways. So one is if you have matter and antimatter, but they're not actually touching, you can bring them really close together. It's possible. Another way is really a particle only annihilates with its own antiparticle. So an electron and an anti-electron will annihilate. A proton and an antiproton will annihilate. However, a proton and an anti-electron do not necessarily annihilate because they, but now that wouldn't be that stable because a proton could, so one of the things is, I didn't get into this, but the particles can decay and particles can be created. So there's always sort of many different interactions, virtual particle decays that are happening where a photon might create a particle-antiparticle pair that immediately decays, so there's sort of effervescent particles bubbling into and out of existence all the time, and this can make it very challenging for even another particle to exist near an antimatter particle. Does time also reverse the antimatter, or only the charge of the particle? That's an interesting question. So for instance, it sort of does. So like a electron, an anti-electron or a positron, it looks like an electron moving backwards in time. So for instance, if you do sort of two symmetry violations, or if you two wrongs to sort of make a right, they sort of cancel each other out. So if you have an electron moving like this way, right, and interacting with something, if you run time backwards, if you replace it with a anti-electron, it looks the same. So yeah, if you run time backwards, you can, if you change also your particles to antiparticles, this is also sort of good. Yeah. Okay, so I will go grab my iPad and walk across the hall. Hopefully we don't get disconnected as I do this, but well, if we do, I'll just kind of run back in here real quick. Okay, and then I think there's a couple more questions that just popped up, but I will answer those as I walk across. So let's see.
Is the audio working as I do this?
Yes, we can hear you.
Okay, good. So yes, I have a very short walk to my lab, and it looks like the laser is on from the safety sign. Okay, so in my lab, I do similar types of experiments to what we talked about when we discussed the electron EDM experiment. However, what I'm focused on is rather than measuring the shape of the electron, I'm trying to measure, you could think of it like the shape of the nucleus. So I'll just sort of give you a rough tour around the lab. Here's one student. This is Josh. She's working on the lasers. I'm giving a virtual lab tour to students in the REYES program. And these are the two, they're called optical tables. They are rather thick, stiff tables that allow us to run laser beams back and forth. And the reason they need to be so thick is because as we put things on the table, we don't want them to deflect and bend downwards and then cause the laser beams that are going from one side to the other to not hit what we've shined them at. So let's turn on some of the lights. Okay. And so yeah, we have at the center of this table is, it kind of looks like a coffee machine, but it is actually a vacuum chamber. So it's a special type of apparatus that cools down the inside of it to a little bit below 4 Kelvin. So it's more like 3.5 Kelvin. And at these very cold temperatures, we can trap particles for very long times, hours or even days or months. And this allows us to measure them for very long times and get very precise measurements. So another thing that's essential is to get the particles and get them very stationary and still, we do what's called laser cooling. So we take laser wavelengths at very particular wavelengths and frequencies, we can actually remove energy from the atoms and bring them to a few thousandths to millionths of a degree above absolute zero. And this allows us to have them be completely stationary and levitated inside of this chamber. And then I showed you a picture of some dots on the first slide. We can look in with our imaging system through the top hole here. And I mean, there's nothing in there right now because we're still building the apparatus, but we would be able to see different single particles trapped and levitated at the center here. So let's check some of the questions. So one person asked if parity and time symmetry are physical in any sense. And yes, they are. So like, for instance, you may, if you've ever looked at, imagine that you took a video of someone throwing a ball and that ball traveled in a nice parabola. So like this, right? And if you just film that ball and then play that video backwards, you wouldn't be able to tell if the video is playing forwards and the ball was traveling like this, or if the video is being played backwards and the ball was traveling like this. In that sense, that system is very nicely time symmetric. So those are real symmetries that you can observe in nature. Now, it's very difficult to run time actually backwards in an experiment because, for instance, you might be able to remember what you had for dinner yesterday, but you probably can't remember what you had for dinner tomorrow. And that's because our brains don't have this time symmetry built into them. Another question is if antimatter is an alternate universe. And I mean, that's another interesting idea. There might be other universes where everything is made out of antimatter and not matter. And because I discussed, parity and these different symmetries are not true symmetries of nature, those universes would behave a little bit differently than ours, assuming that all the physical laws stayed the same. the main problem to me as an experimentalist is I don't have a really good way of actually measuring that, or I don't know of one yet. So I've turned on some of our lasers. Pretty neat. So these are two of the lasers that we use for laser cooling what's called barium ions. And you can see one's blue and one's red, and they're not traveling in straight lines. It's because they're in fiber optic tubes, so little glass strands. And this is mostly for convenience. Normally, you need a bunch of mirrors and lenses to direct the lasers around the table, sort of like as I have over here. This takes up a lot of space, and they're constantly getting misaligned. Here, we can use the principle of total internal reflection to guide the light down this fiber tube, and it just makes it a lot easier and more stable. And it also looks cooler, because usually when the laser is traveling through the air, you can't see it. So for instance, I believe the laser beam is actually exiting this optic here, but you can't see it because it's invisible in air. If I stick this card in, you can actually start to see it. Question, which was, what kind of math do we use in these types of experiments? I know you mentioned group theory, but are there any other topics or classes I would recommend to an undergraduate? That's a great question. So honestly, I don't use that much math. I do like math a lot, and for a while I thought I'd maybe be a mathematician, but I have not really. Well, I know you need some group theory to sort of understand concepts in spectroscopy and also like symmetry. I don't actively employ it when I sort of try to solve problems, not in sort of like the formal extent. The type of math that I use most, honestly, is Fourier transforms. If you can understand Fourier transforms, like really deeply understand Fourier transforms, then you can understand so much about engineering, physics, finance, everyday life. It's just one of the most useful descriptions of things, because it allows you to go between time and frequency, or space and momentum, or this idea that you have two different descriptions of a problem is super useful and allows you to solve so many things. And sometimes I use it formally, where I write down Fourier transforms and apply them. Sometimes I just use it intuitively to think about a problem in a different way. And this is very helpful. So that's a great question. One more. I'm in a country where there's almost no labs. How do I get to work in a lab? Yeah, that's very difficult. So I'm very lucky here. I have a large amount of, honestly, quite expensive equipment. And I was able to start on this path as an experimentalist because I was able to find someone who had a lab that I could go work in. So yeah, if you're in a country without access to labs, one answer might be don't pursue experimental physics. I rely heavily on theorists who can calculate quantities of atoms, who can calculate quantities of different observables, tell me the types of things to measure, give me different theories to test. There's two sides of this coin of physics. You need to have theories that say what are possible explanations, and you need to have experiments that say whether or not these explanations are true or not. And I mean, honestly, theory I don't do because I'm just not good enough at this type of thinking to be able to do it. And I also enjoy working with my hands more. Now there's also, I don't know if you're an undergraduate or graduate student, but you can consider traveling to a different country to pursue graduate work. And so for instance, at Old Dominion University, we have many international students who come here, and I think several of them come without much lab experience. There's also, for instance, REU programs for undergraduates to come to different, I'm thinking particularly in the United States, to come and work in labs here. But there's also, I mean, this is a type of experiment that, well, it's inexpensive compared to the Large Hadron Collider. It's still rather expensive. Many of these pieces of equipment are quite expensive. I would not personally buy any of these. There are types of experiments that are a different order of magnitude in cost. And, different types of science and engineering have different cost entries. So, one of the things that we do a lot of work with actually is Arduinos, which are a low-cost microcontroller platform. So here's one of my students' projects. And so what she's building here is, okay, well, it looks like a bomb, but it's not. There's a microcontroller here. It's a mini computer, and this is an electronic switch. And then this is a temperature sensor. So what we want to do is, there's a part in the experiment that we're going to heat up, but if we heat it up too much, it breaks, and that's really expensive, and I don't want that to happen. Also, it's dangerous. So what this does is it monitors the temperature of that device, and if it starts to get too hot, it'll throw an interlock switch and turn this off. So she built this together and programmed it. But the nice thing is these different components are relatively inexpensive. So this sensor here, it's a very high quality temperature sensor, but it was like $12. And this microcontroller was, I think, $15. And this switch was actually maybe the most expensive. It was $20. But there's also like LEDs here. So these different things can be pretty low cost, are accessible to hobbyists, and they use open source software. So you don't need some complicated software licenses to be able to program these. So I love these types of things, Arduinos and microcontrollers and Raspberry Pis. We use them a lot in the lab, not just because they're cheap, they're also very powerful and they're very accessible. Good. So hopefully that helps. So let's see, some other things I can show you. Maybe I'll say the reason these different lasers are the colors they are. So we have a blue one and a red one, and those are used to laser cool barium. So barium has different electronic transitions, and we need the wavelength of these photons and their energies to match those transition energies to be able to cool them. So we could use these lasers to cool barium ions, but we couldn't use them to cool, for instance, terbium ions. We would need other types of lasers. We also need to stabilize their wavelengths very precisely. So we send them through different optical fibers into this, this is called a wave meter. And here it's actually measuring the wavelength of that red laser. So it's 650 nanometers. And you can see it actually measuring it out to 5 or 6 decimal places. And actually we need it to be stable to more than that. So we're talking like part per million, or really part per billion precision on the energy of these lasers. Yeah. So then we have a variety of other lasers in here. This is a green laser, which I guess I can turn it on, but it just looks like green. I think the blue one's more interesting. There's some other lasers over here. All these lasers I got, they're commercial lasers, which means they're more expensive, but they work very well and they don't require much effort to get started with. Now, lots of people actually build their own lasers, which is a way to make them basically cost 3 times less, although it takes a lot longer. Because honestly, this is just a metal box. Inside of it, there's just a laser diode, which is sort of a very high quality LED. And then there's an element called a grating, which helps provide feedback and stabilize frequency, and then a few optics. And you can build this together, and you need some electronics to control the current through your laser diode. But you can build a laser for, okay, this is going to sound like a large number, only several $1,000s. And this is another good way that some labs can keep costs down. So what we're doing on this table mostly is the lasers that we need to cool and produce ions in this test chamber. And then over here are their optical setups. So these are other lasers that are used for characterization. And this is a vacuum chamber where there's a very precise cavity whose length we reference the wavelength of the lasers to be able to get this extra stability that we need. So for instance, here, this optical setup on the far side is something Josh is working on right now. He's trying to stabilize the wavelength of this laser to an electronic transition in iodine, which is a diatomic molecular gas, and there's some of it inside of this glass cell. So is it on resonance, Josh? Can you get on resonance, or?
The wave meter program's crashed, but I think manually do it.
Okay, well, the wave meter program crashed, and he's going to manually do it. This is pretty typical for experimental atomic physics. You're constantly trying to fix things. And eventually you just have a whole lab full of broken stuff, and you can get things to work once you can fix stuff fast enough. But what his setup here is doing is he's sending this laser through, and it's hitting a mirror, and that's directing it through this glass cell full of iodine. And when the wavelength is just right, the iodine will actually absorb photons, and then because it's in an excited state, it can't hold on to the photons, so it will emit them. But it doesn't have to emit them necessarily in the same direction. It can emit them in any direction. So we'll actually start to see the iodine glow because some of the photons will be emitted directly into the camera here. So we'll see a nice red line here when it's on resonance. So we can detect when that red line is glowing, and that's how we know the laser's on the right wavelength. And the cool thing is because iodine basically works the same as it does here or as it does in, you know, France or Tokyo or like Dubai, then we can use, because iodine has been very precisely characterized, we know what wavelength our lasers is at. And the nice thing is also this cell is not very expensive. I mean, it's very high quality lab equipment, but it's only a few $100s. So it's much cheaper way to stabilize your wavelength than, for instance, some of the other equipment that's in here. So, aha! So you see that. It's working. Thank you very much. So you can see here's the a red line glowing, and that's the iodine that's fluorescing with the laser. Can you scan it on and off resonance? Is that possible? So we're now going to change the wavelength of the laser, and that's going to cause this to pulse. So when the wavelength of the laser is too large or too small, it will glow. Can you change the amplitude? Maybe double it. Yeah, so see how it's not glowing? That's because the wavelength has been scanned too far off. So it stops glowing. And that's how we know it's not the right wavelength. But when it's back on the right wavelength, we can see this line glowing. Great, that's excellent. Thank you very much, Josh. Yeah, and this just looks really pretty. I love this. So that's the lab. And I mean, it's mostly just a bunch of stuff. There's wires, mirrors, different detectors, just a lot of screwdrivers out all over the place. We're constantly building and unbuilding and rebuilding things. A lot of electronics and mechanical pieces we design and build ourselves. If we can get them commercially made, we do that. But usually we build stuff on our own, not even just to save in cost, but because it's more effective. It's a way to get better quality equipment that operates the way that we want. Okay, let me switch back around. So, I'll just one more time. So yeah, I'll maybe take any more questions that people have, and if that's it, then I will sign off afterwards. Okay. Say answer live. Okay. Great. So thank you very much, everyone, for joining the talk and for this virtual tour. And thank you for the very good questions. I enjoyed talking and showing you my lab. Chat. All right, so that's it. Then I'll say goodbye. Yeah, if you have any questions later that you think of, you can please feel free to email me or get in touch with the program. I'm always happy to talk about this stuff. All right, goodbye, everyone.